Yesterday, NASA confirmed something almost unimaginable. Voyager 1 has found a searing wall of fire at the very edge of our solar system. An invisible boundary over 24 billion kilometers from Earth, where temperatures rocket past 30,000 degrees Celsius, hotter than the surface of the Sun itself. Yet Voyager 1, a spacecraft built in the 1970s and powered by mere watts, is not just detecting this blazing plasma barrier, it's traveling through it, untouched. With this single discovery, the place where our solar system ends and everything beyond begins, just changed forever. Why is this wall of fire real, and how does Voyager survive where no human or probe has ever gone before? At 1700 UTC on September 27, 2025, NASA issued a press bulletin confirming Voyager 1's detection of a superheated plasma barrier at the Heliopause, nearly 24 billion kilometers from Earth. The statement cited direct analysis of spacecraft data, reporting temperatures in the boundary region exceeding 30,000 degrees Celsius, 5 times hotter than the Sun's surface. NASA officials described this as a sharply defined, invisible zone where charged particles pile up at the edge of the solar system. The agency clarified that while the term "wall of fire" evokes images of burning, the phenomenon is a shell of ionized plasma, not flames. These findings, verified by cross-checks with Voyager 2, relied on cosmic ray and magnetic field measurements, as the original plasma detector had long since shut down. The announcement stressed that the plasma's extreme thinness allows Voyager 1 to pass through unharmed. Voyager 1's original plasma instrument went silent decades ago, leaving scientists with a challenge: how to measure the temperature of plasma at the solar system's edge without the very tool designed for that job. The answer came from the ingenuity of the current mission team, led by project scientist Dr. Linda Spilker. Instead of direct readings, they relied on the spacecraft's cosmic ray detector and magnetometer, 2 instruments never intended to serve as thermometers. By analyzing abrupt changes in cosmic ray counts and shifts in magnetic field strength, the team pieced together a temperature profile for the boundary region. This workaround, validated by cross-checks with Voyager 2, provided the first direct evidence of a superheated shell at the Heliopause. Every data point represents not just technical adaptation, but a triumph of resourcefulness. Proof that even with aging hardware, Voyager can still deliver groundbreaking science from the frontier. At the edge of the solar system, the collision between the solar wind and the interstellar medium creates more than just a boundary. It forges a turbulent, superheated shell of plasma. Here, magnetic fields carried by the solar wind run headlong into those from interstellar space, twisting and snapping in a process scientists call magnetic reconnection. When these tangled fields break and realign, they unleash bursts of stored energy, heating the surrounding plasma to temperatures reaching 30,000 degrees Celsius and beyond. The result is not fire in any familiar sense, but a zone where ions and electrons are hurled into chaotic motion, their kinetic energy spiking far beyond what steady solar wind alone could produce. According to Dr. Jamie Rankin, current models had predicted some heating at the boundary, but the intensity and sharpness of this plasma shell defied expectations. The energy released in these reconnection events explains why the Heliopause glows so hot, even as the density remains vanishingly low. 30,000 degrees Celsius. Yet Voyager 1 glides through untouched. The explanation lies in the paradox of space: heat without substance. In this region, the plasma is so rarefied that a handful of particles drift in a volume the size of a small room. Even at temperatures that would vaporize metal on Earth, there simply aren't enough collisions to transfer that energy to Voyager's hull. Dr. Jamie Rankin, who led the analytical review, described her astonishment. It's like flying through a blast furnace, but with almost no air, so the heat can't touch you. But the data held another surprise. Instead of a chaotic jumble, the magnetic fields on both sides of the boundary lined up almost perfectly. This unexpected continuity suggests the Sun's magnetic influence stretches farther than anyone predicted, linking our solar system to interstellar space in ways models never captured. The so-called Wall of Fire is not just a barrier, it's a meeting point where cosmic forces remain entangled across the frontier. Voyager 1 began its journey on September 5, 1977, with a mission plan that called for 4 years of planetary exploration. Instead, it has spent nearly half a century pushing outward, crossing the Heliopause in 2012, and now sending data from more than 24 billion kilometers away. The spacecraft operates on just 4 watts per instrument, less power than a nightlight, yet continues to transmit discoveries no one imagined at launch. Dr. Edward Stone, the mission's original project scientist, once said, "Every extra year is a gift to science." Each milestone Voyager reaches now stands as a testament to that legacy. For Dr. Nikki Fox, NASA's heliophysics director, the Wall of Fire discovery isn't just a triumph for Voyager. It's a warning and an invitation. Any future mission, robotic or human, will have to contend with this searing frontier. IMAP, launching in late 2025, was already built to map these outer boundaries. Now, its data will be essential for planning the next leap, when, in November 2026, Voyager becomes the first emissary to reach 1 light day from Earth. On September 27, 2025, NASA confirmed Voyager 1 had measured temperatures exceeding 30,000 degrees Celsius at the solar system's edge, 24 billion kilometers from Earth. This superheated region, now known as the Wall of Fire, is not made of flames, but of sparse, energized plasma where the solar wind and interstellar medium collide. Despite the extreme heat, Voyager 1 survived because the density is so low that its instruments remain unaffected. This direct measurement marks the first time a human-made object has crossed and documented this boundary. Yet, questions remain. How stable is this plasma barrier? And what does its magnetic structure mean for future missions? While the full details of the Heliopause's dynamics are still being studied, one fact is clear. As Voyager 1 continues to transmit data from over 15 billion miles away, its journey is redefining the limits of our solar system and challenging our understanding of the space beyond.